and synthesis of supported catalysts. So we vision from India National Energy Development, along with Costas Goras, my colleague from Oregon State University, sharing this session. So we have about 5 great talks in this session. So without any further ado, let's get started. Good afternoon, Bonito, and it is my pleasure today to introduce keynote speaker, Professor Karen Wilson of Griffith University. She received her bachelor's degree at the University of Cambridge, the one in England, not in Boston. Her master's degree is in Liverpool and her PhD at Cambridge University. She has held multiple positions in many universities in England and Australia, and for the last 2 months she has started a new position as professor of analysis at this university. Join me in welcoming her, and Karen, the floor is yours.
Thank you very much for the kind introduction, and it's been a fantastic conference so far. I think we've all been enjoying it, and it's a pleasure to have the opportunity to present our work to you today. So what I was going to do is just take you on a little tour of some of the work we've been doing designing catalysts for the biorefining. So the motivation for this really stems from the need to move away from petroleum-derived products. And you're probably all aware that the traditional chemical refinery will take crude oil, it'll crack it into the constituent fractions, it will lead to giving you fuel grade, low value or high value products, then higher value, smaller volume fine chemicals. It's the production of chemicals alongside the fuels that makes the economic work. But as we know, if we take fossil fuels and continue to burn fossil fuels, we're going to exceed the 1.5-degree temperature limit in terms of global warming. It's an old diagram I've been showing for a few years, but I think it's quite an important one to put into perspective. The problem is this is the amount of CO2 that you would produce if you burnt all the remaining fossil fuel resources. This is the amount of CO2 you can put into the atmosphere without reaching the 1.5-degree limit. So we can't continue the way we're doing, and we know a lot of initiatives are being put in place to try and tackle this. And one of those initiatives really is to start looking at the use of biomass and feedstock instead of fossil fuels. And the idea being biomass is a circular product, you take waste agriculture, food waste, whatever else, it's plant-based, it's life cycle that takes CO2 out of the atmosphere and CO2 going back into the atmosphere which burns is circular. What we need to make sure though, however, is that the energy inputs in transforming these are not excessive, so that we can actually make sure the process is sustainable. One challenge in the early stages of biorefining was the food versus fuel argument, so we must avoid the use of food-based feedstocks and focus on waste. But ultimately, if we can produce the range of fuels and chemicals, we can make biomass conversion economically viable. But to achieve this, we really need new catalysts because biomass is fundamentally different to fossil fuels. It has high content, and removing that oxygen is the biggest challenge of catalyst design. So if we think about traditional chemical transformations, I think acid is a platform chemical that is used widely in the production of polymers and coatings. Historically, people have looked at putting oxygen in, so selective oxidation reactions to achieve this goal. If we were to start from a sugar in terms of biomass, we would need to look at selectively removing oxygen to get. So in terms of designing processes and thinking about catalysts, we really need to be working with solid catalysts. As we know in green chemistry, hence these catalysts are easier to remove from reactions. We don't want to start more problems by using soluble mineral acids and so on. We produce lots of wastewater. So we need to use solid catalysts. Acid catalysts will feature a lot in biomass transformations, but the problem is that most zeolites, being hydroporous, are not really compatible with the bulky molecules you might encounter in biomass. So we need to think about how we tailor the porosity of these materials. So what we work a lot on is templated mesoporous materials, but then trying to break up those mesoporous networks by putting molecules in there, so to develop hierarchically porous structures where you have large particles that enable rapid diffusion of molecules through the material itself. And then you've got to think about functionality that you want to have on these materials. So the type of transformations that you might want to do, like hydrogen or hydrogenolysis, or then maybe selective hydrogenation and selective oxidation reactions. So we need to incorporate the right functionality to perform those transformations. And because all these reactions are going to be quite complex, this is where the whole cascade thing comes in, we really want to try and combine as many steps in the transformation as we can. So if you want to do a simple deoxygenation, say to make a hydrocarbon fuel, if you're working with an alcohol, your first step would be dehydration of an acid catalyst. Second step would be the hydrogenation step. If we can combine those two catalysts rather than working with two separate ones and have to have separation steps, it will make the process overall efficient. So looking at bifunctional catalysts for cascade reactions is really the direction that we're heading. So what we tend to do is silica is a very flexible material, allows you to generate lots of different pore architectures. But obviously silica itself is not going to have the right functionality. If you're working in water doing hydrothermal processes, silica is sensitive to collapse under those conditions. So what we tend to do is take these silica frameworks and then we will coat them with another philosophy. We've been using a lot of swing-led deposition approaches, starting off with work with the depositing thin metal oxides from the push phase, and more recently we've been exploring the use of atomic layer deposition from the vapor phase to actually grow metal oxides. So for those of you not familiar with atomic layer deposition, essentially what you start off with your support is highly insulated, and then you put in your precursor that is maybe a metal chloride, and it's a self-limiting process where the metal chloride comes in, it reacts with the hydroxyls, and it grafts on the surface. As long as it's dry, you won't get a second layer going down whilst that is a halogenated surface. You then put in another pulse of water that removes the residual chlorine to give you a metal oxide, and then you can repeat that for subsequent coatings. So the idea is you can get layer by layer growth in a conformal way over porous scaffolds. We can do that liquid phase precursors or for the vapor phase. So what we've been doing, for example, is taking SPA-15, coating it with zirconia, taking silicon nanoparticles, coating it with zirconia. And the reason that we picked zirconia is because it's a very hydrothermally stable material. So it's ideally suited to the transformation of biomass molecules in aqueous medium. Zirconia is also very flexible in terms of the range of phases that are accessible. And this actually then opens up unique chemistry in terms of acid-base properties in the surface of these tetragonal or monoclinic zirconia surfaces. Your acid-base strength and distribution will be different. Well, this comes from the production of vacancies in the surface. So if you have, for example, a defect where that might be a Lewis acid site, the adjacent O2 minus in that bridge would be a Lewis base site. So it can open a cooperative catalysis between the base and acid sites in the metal oxide. So we've been looking at how you can grow zirconia films onto these scaffolds and then how we can tune their acid-base properties. And that's what I'm talking about for a pure zirconia sample. Of course, zirconia as well, you can dope it. So if you dope, for example, with sulfate groups, you can introduce strong toxicity, or when that sample gets hydrated, it would be strong bronzed acid. And there's various other dopants you can look at to introduce acidity or basicity into zirconia. So again, it's quite a versatile material. So one of the things we've been looking at in terms of cascade reactions is the production of HMF. If you take glucose and transform that to HMF, it's not a one-step process. The first thing you have to do is isomerize glucose through to fructose, and then you can do an acid catalyzed dehydration to produce HMF. So what you actually need in order to do this is either a Lewis acid or a Lewis base to do the isomerization, and then bronze acidity to do the dehydration. So with zirconia, by partial sulfating the surface, you can get a balance of Lewis acidity and bronze acidity in order to affect that transformation. We've looked at the same type of chemistry on the two-dimensional films grown on SPA 15. This just shows you how well behaved the deposition is. This is actually the liquid phase grafting of zirconium propoxide onto SPA 15. If you look at the XPS, you can calculate what the attenuation of your underlying silicon signal would be as you grow 1, 2, 3 layers of zirconium. Calculate the thickness of that film would be. So the dotted line is the predicted attenuation silicon signal for 1, 2, and 3 layers of zirconia. We can see that the dots, which are the data points, lie very well on that line, confirming that you actually have a nice layer by layer growth. What is interesting though, when we look at these samples by ammonia calorimetry, is that depending on how many layers you've got, you actually have some quite unique acidic properties. So the green dots are the ammonia calorimetry for the heat absorption of ammonia as a function of coverage from layers. A 2-1 layer and then a 3-1 layer. What you can see is the 1, 2 layers is we have a small number of strong acid states. So we believe this comes from the first couple of layers being completely fit. And then once you get 3 layers, it starts to then look like what a bulk zirconia material would appear. So you can, by tuning the thickness of these films, you can tune the acidity of the material. And this also pans out in the catalysis. So again, looking at glucose to HMF, this is the best bulk sulfate zirconia sample with the high coverage of sulfate, the best sort of HMF yield per gram of zirconia. If we look at the graphic systems, you can see that when we have a 2-layer film, then we end up with an overall 3-fold enhancement compared to what a bulk sample would be. So by dispersing the zirconia, we can improve the overall performance efficiency. These zirconia samples can also be used for other cascade reactions, now taking advantage of the Lewis acidity of these materials. Just at the moment in cascade catalytic transfer hydrogenation, in which you use isopropanol as your hydrogen source. Now, in this case, the process advantage really comes from the fact that you don't have to have the hazard associated with using gaseous hydrogen. But zirconia is very effective at this transformation, essentially taking ethyl levulinate, again you can derive from sugars, and turning this into gamma-valolactone. Gamma-valolactone is very attractive, there's a high volume solvent, but it's a precursor to a whole range of other value-added molecules. So traditionally, you can form this using gaseous hydrogen. It requires often high pressures, so there's hazards associated with that. But if you're using high gaseous hydrogen, you may also use precious metals. So what we want to see is whether the zirconia system will work well, and also see if we can improve the process. So many reactions in flow in batch. If we transform to working in flow, can we improve the overall process efficiency? So this is essentially what we've done. We've compared 2 systems. So we have a batch reactor, and just a 1-pot batch reactor looking at about 150 degrees following this reaction. And then the other approach is we've got a continuous flow reactor with our packed bed of our zirconia SPA 15. We feed across this ethyl levolate and IPA, and then monitor the formation of GBL. What we find essentially is that the Lewis acidity of our zirconia SB15 is very effective for the catalytic transfer hydrogenation. But what's most noticeable is when we work in flow, we get a significant enhancement in the cumulative yield of gamma lactone that we do in batch. So in both cases, the catalyst is seeing the same number of molecules of ethyl lactonate. And what we believe is this difference comes from the fact that avoiding reactions itself is still reactive, will undergo secondary reactions. If we're working in flow, then we're also removing the product continuously. Now, it would be nice if we can start to work from the cheaper feedstock. So rather than gamma lactone, rather than ethyl levolate, can we start from levulinic acid? This introduces an even more complex cascade. So what we're going to do is now go from levulinic acid here on the bottom left through the gamma lactone on the right. Now we have various steps in this. If we're reacting with isopropanol, we might have an esterification to form isopropyl lipid molecule. Then it can undergo catalytic transfer hydrogenation to hydrogenate the ketone group, and then it can cyclize and decompose through lactone. But what we can see in each of these steps is we either have steps identified as protein catalyzed, or it's Lewis base catalyzed, which is the transfer hydrogenation step. So again, thinking about we can tune the property until things are zirconia, and we talked about with the glucose isomerization, you would expect to have a partially sulfated surface, sulfated zirconia. We should be able to catalyze the bronzed acid steps, and then we should have Lewis acid base sites to do the catalytic transfer hydrogenation steps. And this is pretty much what we see. If we vary the amount of sulfuric acid used to dope sulfate zirconia, you can see that the first thing that happens if you increase sulfuric acid content is the red lines increase, which is your isopropyl levolate. So the catalyst, as you've got a very high concentration of sulfuric acid, you produce your sulfate zirconia. It's very good at esterification. At the low coverage end, where you've got a partial surface sulfation, you can actually start to see some green dots, which is your GBL. So down here in this partial coverage regime, you're able to have an acid site to do the initial esterification, but still enough Lewis acid and Lewis base sites to do the catalytic transfer hydrogenation. So when you go to very high coverages, you eliminate all of your Lewis acid base sites, and all your catalysts can do that in esterification. So this system, although it works, is quite limited because out here you can see the conversions are relatively low. So we thought, is there anything we can do to try and improve on this? And what we've done, so again, looking at flow reactions, we're thinking about whether we can do a dual bed flow cascade. So in this case, what we thought, we'll take the best catalyst that we've just made, there's a sulfated zirconia for doing esterification, and we will put that in front of the catalyst we used for the previous system before catalyzing the hydrogenase, and seeing basically how, with this dual bed, we optimize esterification and then optimize the transfer hydrogenation through GBL. And what you see is it does actually work. Now, there's a few combinations here, because what actually didn't matter which way round you had the bed. Logically, you think, yes, you have this esterification bed first, it should improve things. We really demonstrate that. And so the system is in sequence we say here, it's attending carbohydrate zirconia first, followed by our zirconia SBA15. You can see you get the highest yield of gamma lactone. So the height of selectivity, gamma lactone is optimum for this system. If we actually do look at, for example, a control, a reverse bed, you can see that is poor. And single bed as well, just sulfate zirconia, is also poor. And what we believe is happening is, again, it comes down to really side reactions, is if you put levulinic acid over the zirconia SpA15 sample, you'll end up with other pathways being violated. So the take-home message really is that we can work these cascades in dual bed in order to optimize process efficiency. Another area of interest in terms of cascades is the production of flumethanol or sorbite from desorbitol. So desorbitol is produced by the hydrogenation of glucose, and then if you do capital dehydration, you produce sorbitol, and then if you do cyclone dehydration, you can produce the dual ring system isosorbite. So both of these are high-value products, and both have applications in, for example, cosmetics or in pharmaceuticals. So again, thinking about the acid-catalyzed reaction, we've looked at sulfate zirconia for these systems. And in this case, what we decided to do was look at the impact of the zirconia phase was on the catalyst performance. So here we've taken tetrahedral zirconia and sulfated it, or we've taken monoclinic zirconia and sulfated that. And we find if you get a different distribution of sulfate groups, that affects their active strength and also their activity. So if you look at the performance of the standard sulfated zirconia just as a function of temperature, you can see that the isosorbide and sulfitan yields increase as a function of temperature. When you go above about 200, you start to undergo lots of side reaction, deactivate the catalyst, and you can see that you get a poor mass balance. The operating temperature is around about 180 degrees. If we look at different phases of zirconia used to produce the active catalyst, you can see that the green and the blue, which essentially are tetrahedral zirconia, are starting from a morphine zirconium hydroxide. Also, when you calculate to a tetrahedral phase, all lie on the same line for acid site loading, and so they will behave very similar. The monoclinic zirconia, however, seems to give you a much higher activity. And what we believe is this is due to the nature of the sulfate species on the surface being very different on the monoclinic surface. So we've looked at this with infrared, and it's quite a complex region for the sulfate bands. But essentially, when you look at the tetrahedral phase, you have two components which are based around the tridentate species, which are labeled 1, and the bidentate species, which are labeled 2, that are sort of overlapping in the spectrum. But for the monoclinic surface, we have a very well-defined set of atoms that seems to stop what we believe is this pyrosulfate-like species that we think is a much stronger acid. And it's this giving us the high activity for the production of the isosorbide through this cyclone dehydration step. So the take-home message really is also that the phase support matters in terms of controlling those acid site densities and actual type of acid sites. Okay, so I'm going to change tack a little bit now and talk about pyrolysis oil upgrading. And again, here we have different cascades that we can look at in terms of trying to stabilize pyrolysis oils, improve yields before you have to start to go and hydrotreat. So this is essentially you're taking your biomass within the cellulose, you heat this up under an inert atmosphere, typically 400 to 500 degrees. You'll end up with a bio-oil. That bio-oil is horrible, sticky like tar. It's comprised of a short chain reactive molecule like acetic acid and aldehyde and so on, furanics. And then also phenolics that come from the lignin component. The problem is all these small molecules make it really unstable. And the acetic acid, for example, makes it corrosive to catalysts. So when you try to do HDO, you've got an acetic acid there, it could potentially deactivate your catalyst. So really what we need to do is a pre-treatment that will remove some of these small components, and then also maybe try to do some chain growth, things like alcohol condensation to improve the hydrocarbon yield. And then once it's stable, treating the oil, then you can do the HDO. So I'm not going to talk about any details of the catalysts and the pre-treatments, but it can give you an idea of the type of reaction you're targeting. So, for example, esterification, decarboxylation would be a way to remove acids from the oil. Again, things like sulfate, the zirconia samples are very good at doing those reactions. Ketonization is another approach which can allow you to grow chains while also removing acidity from the reactions. And likewise, alcohol condensation. So here you might be looking at solid bases or doped solid bases in order to grow chain length via alcohol condensation. And then the final step really is hydrogenation to remove the oxygen from all the components. And there, the use of metal doped solid acids is something that's of great interest. It's that story that I really want to talk to you about on this next slide, is really how we can design a catalyst with metal thrifting in mind. So many catalysts that are used for hydrodeoxygenation often use quite high metal content. So typically you might be looking at, say, 1 to 5 weights in precious metal, because the catalyst itself isn't optimized the process. So what we've been looking at is how we can optimize platinum loading and working with highly dispersed metal nanoparticles in order to improve process efficiency. So if you look at the hydrogenation of anisole over platinum SPA15, we vary the platinum particle size, you can see that smaller particles give you much higher rates. So in this case, what we have though, in the catalyst that stops at this point here, you make very little of the deoxygenated product. So the pathways taking you through to deoxygenation, so that's hydrogenolysis or direct demethylation, are very slow and are minor pathways. The main reaction is ring hydrogenation, and it just gets stopped at the alkali ether. So we know that acids can help CO1 cleavage. So what happens if you add an acid to that system? Well, if you put, for example, aluminum SPA15 in with the methyl cyclohexane, it will actually cleave it to give you cyclohexene. So once we're actually going to the next step, if we run our hydrogenation catalyst, we'll be able to get all the way through to cyclohexane. So if we work with small metal nanoparticles that are optimal for hydrogenation, platinum SPA15, or platinum SPA15, now start to get very clean yields of the fully deoxygenated product. And when you compare side by side the neutral and the acidic supported system, you can see that you get a huge promotional effect in terms of initial rate and also yield of your deoxygenation product. So you increase the cyclohexane productivity for thrills that will produce, but also because of this metal thrifting approach, we're able to reduce the amount of metal needed for the reaction. So when people talk about moving away from precious metals, it's not necessarily needed. Okay, you've got to use the precious metals more efficiently. You don't need to go to nickel, to copper, etc. Just make sure if you're going to use precious metals, use them wisely. Okay. So the last little part of the story I want to talk about is how we can use core architectures to optimize reactions. And we've been working for a long time on the biotransesterification and esterification reactions. So here, for example, you take triglyceride, you react that with methanol and press to the base, you produce your fatty methyl esters. And likewise, if you've got a poor quality oil, you might have free fatty acids there that you need to esterify through to biodiesel. The challenge with these reactions, you're now working with very big bulky molecules, and mass transport through many of the porous systems that we're can be quite poor. So we really need to look at how we can optimize those core architectures a little bit. And the way we've been doing this is to develop hierarchical porous structures in which you start off with your conventional SPA15 like templating solution with chloronic surfactants. But then you add to this a hard template, which typically polystyrene nanospheres that can vary over the range, maybe 100 up to 600 nanometers. And then you sort of process the material, and then ultimately you end up with these monolithic light structures that have large voids where the polystyrene is. And then if you look at the walls, you can see the mesopores where the chloronic surfactant is templated. So these systems, by punching these big holes in the long 2D network of SPA15, enables basically improved mass transport. And we've been able to demonstrate this using relaxation and NMR with our collaborators at the University of Western Australia. But we can actually see with the catalysis the impact of that, of course. If we look at esterification of different chain length fatty acids, so in blue, nucleic acid C3, it can diffuse anywhere. If you look at the longer chains like palmitic and amylic acid, and you can see that we've got various pores, the rate is quite low. You increase the size of the macropores, the diffusion gets improved, and then you increase the rate of reaction. So here, these will all be functionalized with the same active site. We have sulfonic acids onto these. So the turnover frequency should be the same per active site. So the only reason we're seeing a difference in turnover frequency is because the majority of the acid sites are not accessible when you've got diffusion limitation. And we've used it in pulse field gradient NR to actually demonstrate the impact of macroporosity on the tortuosity of the molecule moving through the pores. So here what we looked at is two different pore networks and the diffusion of C6 and C12 molecule. If there's no tortuosity, then these bars should all be without. And you can see that they're significantly higher than that, suggesting that there is some mass transport limitation, but that tortuosity gets less as you go to larger pore materials. And if you look at the diffusion through the mesopore diffusion doesn't change at all. So the molecules move the same speed through the mesopores, but the impact of the macropore is really getting the molecules out of the structure itself. Okay, so we can actually demonstrate now that we do have this beneficial effect. All the materials I've talked about, though, we've burned all the templates out. We've not really been very smart with the design. And what we wondered is whether or not we can actually start to use these materials for acid sites that are spatially distributed, either in the macropore or in the mesopore. And so we've got here, essentially, we modify the synthesis, and we start off with a chloronic material that we've incorporated magnesium sites in it. So we have a metallic surfactant that's chloronic with magnesium, and then our polystyrene is fused. Then we remove polystyrene by refluxing the sample in toluene. So now we have a vacant macropores and our mesopores that are full with magnesium doped chlorine. What this means is we can now start functionalizing the macropores with a different functionality. So in this case, we put zirconia down by the gravity method we talked about at the start. Then we can sulfate it, and we do all this because the mesopore are essentially still surfactants. We can do all of this very selectively, so none of the zirconia, none of the sulfate is going into the mesopore. Once we've got our sulfated zirconia complete, we can burn it all up, and what we're left with is magnesium oxide in the mesopores and our sulfated zirconia in the macropores. So what we have is the hierarchical system. There's acid sites just in the macropores, base sites just in the mesopores. So you could use this for a cascade if you want it, where you had an acid catalyzed step followed by a base catalyzed step. Or as we found out when we submitted the paper, the stream's far more excited about the idea of doing antagonistic reactions. So if you think back to what I showed you with the biorefining synthesis, if you have a waste cooking oil, you have a high degree of fatty acid in there. That fatty acid is in contact with the magnesium oxide of salt, will neutralize base. So the question was, building a material with the acid sites in the metals, can we get a system that is really efficient at esterification, so efficient that it will actually react all the fatty acid to produce an ester and prevent the fatty acid ever getting into the mesopause? In that case, the only reaction we would have going on in the mesopause would be the transesterification of the triglycerides. It turns out the theory worked. So what we have here is looking at the rate of transesterification of our triglyceride. We've got a couple of different combinations here. We have the spatial orthogonal sample, as we call it, with the acids in the lymphopause and the base in the mesopause. We have a physical mixture of two samples made separately, and then we have a sample that's just got the base in the mesopause and no protection in the macropause. So all three of them give you the same baseline activity until you put fatty acid in there. And as soon as you put fatty acid in, you can see these two that have got no protection basically get deactivated, but our spatially orthogonal material keeps working and retains high activity. So the acid sites in the macropause are able to protect the active sites in the mesopause. I'm sure there's many other reactions we can look at this for, but essentially poisonously we want to protect the mesopause sites. So just to wrap up, hopefully I've shown you that we can tune the acid-base properties of materials and platform chemicals. We can look at different engineering solutions, approach intensification in terms of dual bed, blood catalysis, and then the spatial orthogonal idea will also enable you to look at substrate channeling, which will be common to biology, but less in catalysis. So the main people who've worked on the projects, particularly on the polygon and Lee, many constants, different universities who've worked along with our collaborators. A lot of it, there's Zirconia, MEL, Luxa, had a display here. We have a lot of their Zirconia as well. Just quickly, the lot of people say, where's Griffith? I just want to tell you where we moved to. So this is Australia. Griffith is near Brisbane, so right on the Gold Coast, on the east coast of Australia. Beautiful city, close to the beach. You're all very welcome to visit if you ever get a chance to come to Australia. But as a university, it's highly ranked on science and engineering, which historically had a centre for catalysis, which basically is an interdisciplinary centre that spans all areas from electric catalysis, photocatalysis, and we're bringing now the sort of green chemistry and sustainable chemistry aspect to the university. And most importantly for any PhD students who are thinking about what to do next, we are actually hiring. So we have a new centre which has been funded by the Australian government to sort of centre in the US. It's a 7-year programme looking at electrochemical and transformation of carbon dioxide to higher value. So if anyone is interested in a postdoc in Australia, then please do get in touch. And finally, last plug, I'm Associate Editor of Sustainable Energy Fuels. Anyone who's working in the energy field, whether it's biofuels, electric catalysis, photocatalysis, if you're interested in submitting papers to sustainable energy fuels, we cover all of those areas. And finally, thank you for listening.
So, questions for Karen? We have a couple of minutes for question.
Show the odds provide production size students, particularly with respect to the pharmaceutical yes. And can you ever attempt to deny that? Go all the way to the pharmaceutical?
No. But again, in terms of the thinking about the event, it's not something where you then have separately. Yeah, I mean, and then they up. It didn't look further.